Every time you generate an image, prompt an AI, or stream a movie, you are creating physical heat. Multiply that tiny thermal output by millions of servers packed into a single massive warehouse, and you generate a fiercely concentrated thermodynamic footprint. Look at this blueprint. Engineers use mathematical models like this to calculate heat load estimation, projecting exactly how much thermal energy a facility will produce on day one and years down the line, before the foundation is even poured. If that intense, concentrated energy isn't continuously and rapidly extracted, the hardware keeping the digital world online would literally melt down in a matter of minutes. A standard office building just needs a gentle breeze to keep humans comfortable. A high-density data center requires extreme, continuous thermal extraction. To prevent equipment failure, facilities rely on raw industrial scale, pumping massive volumes of frigid air through the complex every single second. The baseline defense utilizes massive mechanical systems, CARAC units, which stands for Computer Room Air Conditioning, and CRA, or Computer Room Air Handlers. These machines push air over coils cooled by large chilled water systems, or direct expansion systems, known as DX, which use chemical refrigerants to pull heat out of the air before it is blasted toward the servers. This brute force cycle of forcing chilled air in and sucking hot air out keeps the hardware functioning, but it requires staggering amounts of electrical power to keep the massive fans and compressors running. Simply blasting a room full of cold air has a severe engineering flaw. The blistering exhaust leaving the servers inevitably collides with the fresh incoming air, immediately neutralizing the cooling effect. This diagram illustrates the problem. Notice the swirling red and blue arrows combining into that inefficient purple zone. To solve this, facilities employ a strictly structural solution called hot aisle, cold aisle containment. First, the server racks are reorganized so that the fronts face inward toward each other. This creates a dedicated central channel strictly for pulling in cold air. Next, the backs of the racks vent outward into opposite aisles, forming a completely separate zone designed exclusively to collect the hot exhaust. Finally, by capping these rows with sliding doors and physical ceilings, the zones are completely sealed off. The hot and cold air loops are physically blocked from ever mixing. By simply manipulating physical space, engineers dramatically drop a facility's overall energy consumption without touching a single piece of the actual cooling machinery. The next engineering hurdle is control. Running huge industrial compressors at maximum capacity all the time is wasteful, so facilities have to operate them only when mathematically necessary. One major strategy is free cooling. By building data centers in freezing climates or next to deep bodies of water, facilities can pull in natural outside air or local water to chill the building, bypassing the need for power-hungry mechanical compressors entirely. For precise internal control, facilities install thousands of highly sensitive environmental sensors directly onto the individual server racks to monitor temperatures down to the square inch. This granular data feeds directly into variable speed drives, or VSDs. Instead of blowing air at a constant blast, VSDs dynamically spin the fans faster or slower, matching the exact real-time demand of the servers. Modern thermal management is a constantly recalibrating equation, continuously balancing massive computational heat loads against the steep financial costs of electricity. The latest generation of ultra-dense AI processors generates an extreme, localized heat load that older chips never reached. We have hit a hard physical limit. Ambient air is simply too thin to absorb and carry away this severe concentration of thermal energy fast enough to stop the hardware from failing. This requires a shift to liquid cooling. Specialized fluid compounds are significantly denser than air, allowing them to capture and transfer heat thousands of times more efficiently. Here we see a direct-to-chip setup. A specialized cold plate mounts directly onto the processor, piping microtubes of engineered coolant right over the hottest cores to pull thermal energy directly out of the silicon. With massive AI workloads, waiting for a temperature spike to happen before reacting is a mathematical gamble. Software has to take over where mechanical cooling reaches its limits. Facilities now use AI-based cooling optimization to constantly analyze vast streams of historical and real-time environmental data across the entire data center. This map shows that AI operating in real time. It can predict incoming computational workloads, and instantly push extra cooling capacity to specific racks, preemptively icing the exact hardware zone moments before the data spike hits. The ultimate ceiling for global computing power is no longer determined by chip manufacturing speeds. The true limit is our ability to intelligently engineer away the heat left behind.